Okay, welcome to another live session for the online class, the last of the year. In the new year, I'll be in London on sabbatical, well deserved. Don't know why I chose a cold, damp, and dark place. It's my homeland though, and London is a lot of fun. I'll be working at Imperial College, and we're planning on continuing the live sessions using slightly different technology and roughly with the same frequency. So we look forward to that. Meantime, I'll be happy to take your questions.
All right, our first question is from a live viewer. Henny asks, how do we know the half-life of radioactive materials?
So radioactive materials are based on the instability of a massive atomic nucleus. So the most stable atomic nucleus is iron. So atomic nuclei have a sort of binding energy curve where when they get very massive, the number of neutrons exceeds the number of protons, and that leads to instability where the nucleus can essentially split apart and form daughter nuclei. So this process is governed by nuclear physics. It's very reliable, and so for a given isotope or element, the half-life, which is the time it takes half of the atomic nuclei of a sample to decay, is a very well-determined number. So for uranium-235, I think it's about 4.8 or 4.5 billion years, roughly the age of the Earth. And then for the carbon, radioactive carbon that's used for dating living samples of material, it's tens of thousands of years. So depending on the mass of the isotope, half-lives can range from thousands of years to billions of years, actually to trillions of years. And how we know that is essentially by direct observation. It's by taking the isotope, observing it in the lab, measuring the mass and therefore the number of atoms or nuclei extremely accurately, and then seeing how they decay to their daughter, the parent and daughter nuclei. That's the phrase for what happens after the decay process. And since that's a statistical process that's very well determined, it means in the real world, a sample of material, if you know roughly when it formed and you know that the atoms were essentially locked in place in the formation process, then by looking at the fraction of the sample that is decayed, then you can deduce how much time that sample has been present and therefore its age. So it's a pretty robust and standard method for determining the age of everything from living material, tens of thousands of years, up to the Earth itself, of course, and the Moon. Their ages, which are known to less than 1%, it's 4.54 billion years plus or minus 1%, or a few hundred million years, actually a few tens of millions of years, is a sign of the precision of that method.
Right, the next question is from a live viewer. David asks, is there any plausible theory of how Mars could have changed from a planet with running water to the state it is in now?
There are plausible theories, but actually none of them has been very well validated by the data we have so far. So the general idea is that Mars was warmer and wetter in the past. There's this very strong indirect evidence that Mars had standing bodies of water, shallow lakes and rivers and so on. And the evidence, of course, you can age date that evidence. These are old surfaces showing signs of erosion, and there are geological formations that indicate sedimentation, which only occurs in a liquid, presumably water. And so 3 billion years ago, we find many of these surfaces on Mars. Mars, of course, is also geologically active, although less active in the recent past, last billion or 2 years. So some of the evidence of water and running water and standing water is, of course, removed by volcanism. But enough of Mars is as old surface that we can see signs of liquid water. So the evidence that Mars had standing bodies of water 3 billion years ago and perhaps as little as 2 billion years ago is very strong. We know what Mars is like now. Mars is an arid desert. The atmospheric pressure is 1% of that of the Earth. It's almost entirely carbon dioxide. It's extremely cold. Liquid water cannot exist on the surface of Mars now. So the question is, what happened? And actually, there's a couple of Martian missions. A couple of the orbiters are really designed to look at that question. What happened to Mars' atmosphere? So Mars is, of course, a low-mass planet, much smaller than the Earth, and therefore much less gravity. And over time, it will lose its atmosphere. So if Mars originally had a denser atmosphere of carbon dioxide, the same component that it has primarily now, it will gradually lose that into space. And of course, then the heating effect, carbon dioxide being a very efficient greenhouse gas, will be lost. So as Mars naturally loses its primordial atmosphere, just due to the evaporation essentially of those molecules into space, the temperature will go down because the heating effect is lost. And of course, there's no insulating effect with the thermal blanket of an atmosphere too. And so at some point, it will be impossible for water to be liquid on the surface. The trouble I alluded to, however, is that the detailed models of Martian climate change don't quite explain. They don't explain either how much warmer it was in the past, and was it really warm enough to hold bodies of water, liquid, on the surface. And they also don't explain why it changed as dramatically as it has to the present day. But that's the general scenario that people tend to believe.
Right, our next question is from Aya, who is on with us live, who asks, do radial velocity readings and transit readings interfere with one another? And I'm assuming they mean for exoplanet detection.
Right. So these are the two primary methods of exoplanet detection and characterization. The first to be used was dating back to 1995, 51 PEG was the radial velocity method. The first transit detection of an exoplanet, I think, was 1999, so just a few years later. And of course, Kepler was so successful that most of the exoplanets known have been found by the transit method. Actually, rather than interfere with each other, I'd characterize the relationship between these two methods is that they complement each other and reinforce each other. So the radial velocity method, of course, is based on spectroscopy, and it immediately gives the orbit of the exoplanet based on motions measured of the star that the planet orbits. So it's a reflex motion. And if you have a radial velocity measurement of an exoplanet, you immediately have its orbit from the amplitude of the radial velocity and the known mass or size of the star it orbits. You have the mass of the exoplanet. So you have two crucial pieces of information: the orbital time, and thereby, with Kepler's laws, you know how far it is from the parent star, and you know the mass of the planet. The transit method also gives you the orbital time, because if it's a transit where it eclipses its parent star, that will repeat with the orbital time scale. So you also get the orbital time. And crucially, you get the size of the planet, because the amount of the dip in the eclipse is basically the ratio of the cross-sectional area of the planet to the parent star. So again, you do have to know what the parent star is and what kind of a star it is to know what its cross-sectional area is. Now, the reason these are valuable to have together is that if you know the mass and the size of a planet, then you can get the mean density. And that's your first step towards characterizing the planet. If you only had the size or you only had the mass, you wouldn't know what the planet was made of. You could speculate, but you wouldn't know. But if you have both, and that information, the combination of that information is known for over 200, perhaps as many as 300 exoplanets now. So less than 10% of the total, but a very important 10%. Now you can characterize the mean density. And then that allows you to say roughly, at least, whether it's a rocky planet, perhaps an icy, watery planet, because ice is less dense and less massive per volume than rock, or a gas giant, a Neptune or a Uranus type object that's mostly hydrogen and helium. Now, it doesn't really let you characterize a hybrid situation where you have a metallic core and a rocky mantle and maybe water around it and then gas around that, because as soon as you have multiple components and one piece of data, which is the mean density, you're kind of lost. So you can't make many predictions. But the two pieces of information together are extremely valuable.
All right, our next question from a live viewer, from Jane, asks, what kind of new telescopic lenses are being developed?
So telescopes in the modern era of research astronomy don't use lenses typically. They're almost all mirrors. So the classic telescope from Galileo's time was a lens, a refractor. And the last great refractor was the Yerkes refractor, which is about 1 meter. That's an incredible sized lens if you think about that, and that's just outside Chicago. And that hasn't done research for some number of years. So refractors are not cutting-edge research telescopes anymore. It's very, very hard to make a lens bigger than about 1 meter across because it's going to be convex, and so in the middle it'll be very thick, very heavy, and it'll sag literally because glass is not a perfect solid. It actually does move slightly over time. So the telescopes that we all have around us that are used on the major mountaintops are all reflecting telescopes with parabolic shaped mirrors, including ones that we make at the Mirror Lab here under the football stadium at the University of Arizona. Lens telescopes are still used, but mostly in the amateur domain and for small telescopes for recreational use. There is, of course, a modern version of the Galileo telescope called the Galileoscope that was developed for the International Year of Astronomy in 2009, which was the 400th anniversary of Galileo's use of the telescope. He didn't invent it, but he used it for astronomy. And the modern Galileoscope, which you can still buy online, and you probably need a tripod because the field of view is very small. It's hard to hold it still. That does use lenses, but it uses modern, cheap, and high-quality plastic lenses that were never available hundreds of years ago when you had to use glass. So that's the way in which refracting or lens telescopes are still used.
All right, our next question from Kathy and Art, who are on with us live, asks, please clarify whether gravity is a fundamental force or the result of the warping of space-time.
I think the answer is both. It is a fundamental force, and physics only knows of 4 fundamental forces, of which gravity is by far the weakest. And then the next ones up are the electromagnetic force, and the weak nuclear force responsible for radioactivity, and the strong nuclear force, which holds basically quarks inside the nuclei of atoms in protons and neutrons. And all the work of the last half century has not found any other force of nature. So we only know of those 4 forces, and gravity is one of them. However, the conception of gravity in the hands of Albert Einstein and the general theory of relativity is that instead of thinking of gravity as a force acting somewhat mysteriously across a distance, instantly holding planets around their stars and stars orbiting their galaxies, it's a little strange to think of that concept, but that's what Newton had, is replaced by a situation where the presence of mass or energy, remember they're equivalent due to Einstein's other work on E equals mc squared, the presence of mass or energy warps space-time itself. So mass and energy are hyphenated and equivalent, and space and time are hyphenated or coupled. And so Einstein's conception of gravity does sort of replace the classic Newtonian idea of a force acting across a distance to hold 2 objects together, with vacuum in between, with a more interesting idea that the presence of mass and energy warps space-time, and then objects traveling through that warped space-time have curved trajectories according to the bending of space-time. And that's the theory of general relativity, and it's a very successful theory of gravity.
The next question from Alexandra, who's on with us live, asks, can you replace adaptive optics with neural networks or other computer algorithms?
So neural nets and other computer algorithms, machine learning, they are used in astronomy quite extensively. And in fact, to do adaptive optics, you're not necessarily, you are using a sort of version of a neural network, but at some level you can't replace the fundamental hardware that sits at the end of the telescope. So those kind of processes, downstream processes, can indeed be used in making a very sharp image. But the key piece of this is what you put at the end of the telescope. So basically, you have to figure out how the atmosphere is distorting the light as it passes through the atmosphere and is collected by the primary mirror. And then into the secondary mirror, which is a thin, flexible shell, moving very quickly, 100 times a second by small piezoelectrically controlled actuators, you adjust that surface to exactly compensate for the fluctuating path length of, and deviations of light traveling through the atmosphere. That's what adaptive optics does, and that's the physical mechanism by which you compensate for the atmosphere. Now, how you combine that information, how you put all that information together to produce a perfect image, that can involve a neural net. That can actually involve a learning algorithm that learns how to take what is really a large amount of information in the focal plane of a telescope, which has to be processed, again, 50 or 100 times a second. So it's a large amount of computation. That's something neural nets are very good for, to produce the optimum image size. And for a point source, you know what the image size and shape should be. You know what the response of a perfect telescope to a point source is. So you know what the answer is, and that helps you train your neural net.
All right, the next question from one of our live viewers is, has anything changed regarding the James Webb Telescope launch?
The only thing that seems to have changed is it keeps getting pushed off. So we're talking, I think, October 2021 now, which is rather discouraging for people who expected, well, that it would already be up now. It actually should have been launched a couple of years ago. So the James Webb Space Telescope has been multiply delayed. Its price tag went through the congressionally mandated ceiling of $8 billion actually a couple of years ago. So it's now on sort of cost override mechanisms, which are pretty uncomfortable. There's no inclination to cancel a project with so much money spent and all the hardware essentially in place, undergoing its last tests. But the truth is, it's a pretty awkward situation because the final bill is not in, and it will exceed $10 billion by the time of launch. And then, of course, you have to operate that telescope for probably a decade, maybe 15 years, pay people to do research with it, publish results. You don't have to mess with the instruments. Once it's put at its situation, it's unserviceable by astronauts, so at least there's no cost there. But you have to run a ground station, you have to run a facility to control it from the Earth. And so there are significant ongoing costs in a project like that. What was new, of course, over the summer and very uncomfortable for people involved in the project was that in the shake test that it underwent to simulate the violence of a launch, where you can have components that are suffering tens of Gs of forces, pieces started to fall off the larger assembly of the telescope, indicating they had to go back to not the drawing board or square one, but actually to figure out what adhesive they needed to make sure small pieces wouldn't come off the telescope during launch. So that's a big setback. Some of the instrument tests have been a little awkward. High noise levels have been seen, but none of those are fundamental, and none of those will impede the launch. It's pretty hard to imagine it slipping more than it has already.
All right, the next question from one of our live viewers is, can planets orbit black holes?
Definitely. They can, and we don't know if they do or if we can detect them. People sort of forget that the very first exoplanets to be discovered was not the famous 51 Peg detection in 1995. The very first planets to be discovered were a pair, and eventually a third was found, of pulsar planets. So the first planets were found 3 years before 51 Peg, 1992, and they were orbiting a pulsar. And so slight irregularities in the pulsar frequency indicated a companion orbiting and disturbing the pulsar orbit. So that was the first detection of exoplanets, was around a pulsar. So if planets can exist around a dead corpse of a star, a pulsar, then there's really no reason in principle why they can't also exist around a black hole. We don't have, pulsars are particular objects. They have little searchlight beacons of radio waves. And so when you detect the radio waves sweeping through your radio telescope every orbit, you have an extremely precise marker of the frequency of spin of the pulsar. Black holes have no such marker that we know of. So there's no way to use a black hole spin and deviations about its mean spin rate to infer the presence of planets. So yes, black holes might have planets. A dead star, we imagine if the planet was ever living or habitable, it would never have survived the supernova explosion that preceded the creation of the black hole. So these are, it's a corpse of a star, and it's probably a corpse of a planet if it exists, but they definitely could exist.
All right, our next question is from another live viewer. They asked, do I need to have a PhD in order to get a job as an astronomer, or MTech in engineering physics is sufficient? Is that sufficient?
It's tricky. So getting a PhD, I'll just give the demographics of our field. And our program here in Arizona is typical. We have 45 graduate students. So most 90% of the students who come into our PhD program in astronomy or astrophysics, in other places it's called astrophysics, and we do that too, have bachelor degrees in science and almost always in physics. So the core qualification for doing astronomy or astrophysics is physics. And along the way, when you do a degree in physics, you learn a lot of math. So there's 30% of your curriculum is math. So it's basically math and physics. Some people do undergraduate bachelor's programs in astronomy, but even then, that's the title of the bachelor's degree, is going to be based on a lot of physics and math. Now, because that's the bulk of the people and the path towards a PhD, that sort of implies that's how you have to do it, but that's not strictly true. I know of, and we've had in our program, people who've come into astrophysics from an engineering background. I mean, basically, if you have a strong technical background, including the requisite math, which means up to the level of calculus and differential equations, then you can handle the curriculum of an astronomy PhD program. You might be missing some core astronomy content. That would mean you may have to take some refresher courses or some courses in the summer before a PhD program. And some PhD programs are structured so that sort of astrophysics and astronomy background that people didn't necessarily get as an undergrad is dealt with early in the 2 years of coursework. So there's no one path. There's a preferred path and there's a typical path. But with suitable engineering and technical background, you could be a competitive applicant for a PhD program.
All right, our next question is from a live viewer. Bren asks, how big was the star that made the supermassive black hole at the center of the Milky Way?
So that's an interesting question, because actually we think that the supermassive black holes in the Milky Way and all other galaxies were not formed from a single dead star. So remember that this classic type of black hole, the dead star corpse, forms from the death of a massive star. It's what's left over when the core collapses after a massive star lives its life. And we think that the most massive star you can have formed by any collapse of a gas cloud is about maybe 200 times the mass of the sun, and maybe only 150. If a gas cloud more massive than that forms, it will collapse and get very hot, but it'll collapse so violently it blows itself apart. So we think there are no stable stars above about 150 times the mass of the sun. Such a star, if it lives its life, will lose a good part of its mass, to half to 2/3. And so we therefore also think that the most massive black holes that form from star death are 50, maybe 70 times the mass of the sun. So that's as high a black hole mass as you can get from normal star death. The black hole in the center of our galaxy is 4 million times the mass of the sun, an entirely different beast, orders of magnitude bigger. And so it could not have possibly formed from a single star dying. In fact, we think the black holes in the center of galaxies form in an entirely different way. They form in dense regions of space where there are a lot of stars naturally, because it's the center of a galaxy. And so if early in the history of the galaxy you had a seed black hole that might have been about the size of the largest dead stars, so few hundred times the mass of the sun, maybe up to 1,000 times the mass of the sun, then over time, that seed black hole will gradually accrete material, devour gas, devour stars whole, or rip their atmospheres off and eat the gas. And so because of the large amount of fuel available to a black hole in the center of a galaxy, it's a very dense region of space with stars and gas, that black hole can grow very rapidly. But it grows rapidly through the accretion of gas, just gas itself, or individual stars. It's not really ever been a single star that just grows and gets big.
All right, our next question from Bren, who's on with us live, asks, how is it possible to see the stars that are orbiting Sagittarius A star through all the distance and dust? It seems impossible.
It was impossible until about 30 years ago, when infrared imaging techniques matured. So you're right, it is impossible. If you ask, can we see in visible light the center of our galaxy, the answer is no. I think the actual number is 1 in a trillion photons from the center of our galaxy, Sagittarius A star, reaches us at the Earth's position. And that's just because, as you alluded to in the question, the amount of gas and dust between us and the galactic center, 28,000 light years of it, extinguishes visible light. However, the extinguishing effect of dust and gas diminishes with increasing wavelength. And so by the time you get to radio wavelengths, the center of the galaxy is transparent. You can see clear through to the center of the Milky Way, and we know that the most compact radio source known is at Sagittarius A star. But all you have to do is actually go a factor of 3 or 4 in wavelength longer than visible light to about 2 microns or 3 microns, the near infrared as it's called, and the amount of extinguishing by dust has gone down by a couple orders of magnitude. So there's still opacity there, there's still extinction of the light and loss of radiation, but it's now not so dramatic that you can't detect it. And so when those, and so that was one thing, you had to go to longer wavelengths. And the other is you actually had to have infrared detectors that could look at a significant chunk of sky. When I was coming up through astronomy 30 or 35 years ago, infrared detectors were single elements. They're just 1 pixel infrared detectors. They came from military applications and they were very finicky and experimental. Now, infrared CCDs, infrared arrays, are just as good and reliable and almost as big as optical CCDs. And that started to happen in the 1980s. And so the mid to late 1980s was when astronomers, particularly a group at UCLA under Andrea Ghez, and a group at the Max Planck Institute in Germany under Reinhard Genzel, started to do systematic observations of the galactic center with infrared arrays and just started for the first time to map out the orbits of stars nearby. Now they've been doing it for a couple of decades and they've seen entire orbital periods. There's a couple of those stars that have orbital periods of about a decade, and they're actually starting to see the 3rd complete orbit of those stars. For other stars a little further out or in different trajectories, they've only seen fractions of an orbit. But either way, each of those stars is a test particle, to use a physics term, for measuring the mass of the central black hole. And each of the stars they look at indicates a mass of the black hole. So you have all these independent measurements of the mass of the black hole in our galaxy from these various stars. Very powerful method, but it wasn't possible until a couple of decades ago.
All right, next question from a live viewer is, there are gaseous planets, so is it possible to have a gaseous moon?
If the moon is big, and then we get into the semantic distinction between what is a moon and what is a planet, what is the boundary between a moon and planet. Astronomers tend to answer this by saying, well, a moon is something that orbits a planet, and so it obviously is smaller than a planet, but how much smaller? The smallest mass ratio between a moon and a planet in the solar system is between our moon and our planet, the Earth. Most other moons in the solar system are much smaller relative to their planet mass than our moon is to the Earth. So yes, if you had a big enough planet with a big enough moon, it could have an atmosphere. And we already know of examples like this, because in the outer solar system, we have Jupiter and Saturn, the 2 most massive planets, each of which has moons with atmosphere. Maybe the most striking is Titan, which is a moon of Saturn. And Titan has an atmosphere that's eerily similar to the Earth's atmosphere and made of mostly the same thing. It's made of nitrogen. And it's also as thick as the Earth's atmosphere. I think actually at the base of the Titan atmosphere, the atmospheric pressure is twice that of the Earth. So absolutely, a moon can be large enough, and it doesn't have to be as large as the Earth or as most planets in the solar system to be able to hold an atmosphere that's quite substantial. And so yes, we would imagine that exoplanets that we measure have atmospheres, and many of them will have moons around them, exomoons, and some of those exomoons will have atmospheres too. And astronomers are actually trying to push their methods to try and both detect exomoons and characterize their potential atmospheres.
All right, our next question from a live viewer is, in an expanding universe, is the repulsive force from dark energy strong enough to overcome the gravitational forces on the scale of galaxies or even solar systems given enough time?
It's an interesting question, and it comes down to our knowledge about dark energy, which is very rudimentary. So we don't know what the nature of dark energy is. So it acts as a universal repulsive force, and therefore the what effect it has on space-time is to make space-time expand at a larger and larger rate. At the moment, the level of dark energy we see in the universe around us by measuring the accelerating expansion rate is not going to overcome the gravity that holds together galaxies or solar systems. So the dark energy we see at the moment is not strong enough to disrupt the binding of objects by gravity into, systems of stars or even systems of galaxies. But we don't know if dark energy changes its properties over time. At the moment, the best guess and the best measurement is that dark energy accords with Einstein's cosmological constant, which means that dark energy is sort of independent of time and space. The strength of it doesn't depend when in the universe you look, and it doesn't depend on which direction you look. So it doesn't vary with direction and location in the universe. There are some models of dark energy, as little as we know about it, where the strength of the dark energy increases over time. And one of these scenarios, which got a lot of media attention maybe 6 or 7 years ago, is called the Big Rip scenario. And in the case where dark energy increases with strength over time, then the accelerating expansion of space-time propagates down in scale to the level of galaxies, at which point galaxies are ripped apart, and then to the level of solar systems, at which point solar systems are ripped apart, or the planets are ripped away from their stars. And eventually, in a crescendo, it cascades down to objects like us, or the Earth, or humans, or even individual atoms. And that's where it becomes the Big Rip. It rips apart matter. Everything we measured so far does not indicate we live in a Big Rip universe, or that we have dark energy with those properties. And so, no, the dark energy that we think we can measure is not going to disrupt everything in the universe over time.
All right, our next question from a live viewer is, NASA released audio which was recorded by the InSight lander on Mars. Can you explain what that is and how it was done?
Yeah, I mean, this was NASA thinking ahead. I mean, the InSight mission is designed to do a number of things, but it's fairly cheap in terms of mission design. The instruments they put on a Mars lander are complex and can be heavy. Even a camera is a heavy device and significant expenditure. But to put audio detectors, microphones if you like, they can be made tiny, piezoelectric, really small, almost miniaturized. So it was very easy for them to build in the ability to create, to detect sounds or variations in atmospheric pressure that approximate a sound. And we know Mars has a thin atmosphere, but we also know it has a very active system of weathers and winds and dust storms and so on. And so the InSight lander was, creatively designed to include the ability to detect the subtle sounds of the Martian atmosphere and dust storms or winds should they arise, and then turn those probably inaudible and probably mostly very low frequency sounds, upscale them to the frequency range that human ears can hear, and boost their strength so that you make a soundtrack essentially to Mars, or it's called sonification, where you turn a signal that's not directly audible into an audible signal. So the things that have appeared on the internet in the last few weeks are really nice because they are scientific data. They're real detections of sound on Mars, but they have had to be altered, modified, boosted, and frequency shifted to be able to hear them.
All right, our next question is from a live viewer, and this is going to have to be, we'll have one short question after this, but this is going to be our last question. Comets that are made of ice and dust and lose material when they're close to the sun and produce meteor showers. How come asteroids that are made of rock also release material when they're near the sun?
It's not uniformly true because we don't know much about the composition of asteroids in general. But a hint is that when you look out in the asteroid belt and you measure the shapes of asteroids, you find a significant number of dumbbell-shaped or highly elongated asteroids. And those double asteroids, as they're typically called, are as a result of collisions. And so they're sort of loose, weak collisions where the gravity holds the object together, but it's not fully fused. And so asteroids seem to be composite objects. They form by collisions, and sometimes that's really obvious. And they don't have the full structural integrity of a fully formed planet, where the gravity is so strong that it crushes the rock into a sphere. Of course, full-size planets tend to have spherical shapes, a lot of internal gravity. Since asteroids have weaker gravity and they've often formed by collisions and mergers, those processes can be overcome when there's a lot of extra radiation. So when an asteroid is on an Earth crossing trajectory or ends up going near the sun's radiation and even just changes in its orbit can cause the asteroid to come apart, and pieces will come off. And also, so they're not really dust piles, but they're not completely solid integrated rocks the way you might think of the Earth being. And so that's why we see them get quite active and interesting when they're close to the Earth and near the sun.
All right, the last question is about our course, and I thought this would be a good time to mention our new course that's coming out in February. Yes. But the question is, hi, I'm thinking of doing your course, but I don't know a lot about the universe or solar system. Is your course difficult, and is it mainly scientific?
So we have a new course that we are going to launch pretty much a month from now. It's coming out in the new year for Coursera, and it's called, what was the title? I now forget our astrobiology title. Matthew, do you remember the title?
It's an astrobiology course.
But it's an astrobiology course. Just look for the title, look under my name, and will be 3. I'm associated with a biosphere course too. So it's an astrobiology course launching in January on Coursera. You should start to see the publicity material, like the trailer. We shot a short trailer up pretty soon through the University of Arizona. You can also search for the University of Arizona Coursera homepage, which will show the not large number of MOOCs that we have. So we're looking forward to that. And no, you don't need background, although it's about exoplanets and life in the universe. It does not require previous astronomy, does not include mathematics. It's essentially non-technical, but the concepts are pretty high level. And so I welcome all of you to check that out in the new year.
And the course is called Astrobiology Exploring Other Worlds.
Astrobiology, Exploring Other Worlds. So thank you for being with us through the year, and have a great holiday, and we'll see and hear from you in the new year. Goodbye.